So today we'll be looking at the first is the final energy consumption, that is the global final energy consumption. Okay. And then installed capacity and electricity generation, the need for renewable energy. Then we'll look into solar energy. So there are two types of two ways in which we can extract uh, power or energy from solar, which is, well, first is photovoltaic or PV, and then the second is thermal, right? Then we'll look at wind power and what that entails, some concepts related to power and energy, and then we'll go on to the Q&A. So looking at the final energy consumption, sorry, this is for India, it's not global actually. So in India's final energy consumption amounted to about 600 million tons of oil equivalent. Okay, so what does this mean, million tons of oil equivalent? So basically, if you are burning oil, that is crude oil, basically, the number of barrels or the number of tons that you burn, the equivalent amount of that. So, for example, if you have electricity, the amount of electricity you consume, an equivalent amount of energy by burning this oil. So that comparison is basically the million tons of oil equivalent. So let's say I say that, okay, 1 megawatt of electricity. So what does that entail in terms of oil? Right. So that is million tons of oil equivalent. So this is a very commonly used unit actually in global energy terminology. So out of this is 600 million tons. Industry and residential sectors accounted for over half. Okay, so these are the areas that we need to focus on if we are. Yeah. Did someone have something to say or? Okay. Yeah. So these are the areas that we need to focus on for efficiency improvements or for targeting, renewable energy substitution and so on and so forth. Right. So in India, so if you look at the installed capacity of power generation sources in India, so more than half, I mean, just about half of it is from coal. Okay, and the others, let's say even okay, you can even consider lignite as coal, right? That's also coal basically. So you also have gas and diesel. So altogether, it accounts for more than about close to about 60%. Okay. With the rest, about 41% coming from renewable energy. That encompasses, solar, wind, biomass, waste to energy, small hydro, and nuclear, right? So nuclear is not exactly renewable energy, but it is a clean source of energy. So that's why it is there. Let me ask you this. Biomass is about 2%, like you can see in this pie chart here. So what does this biomass entail as an energy generation? Do you know where it is being used? What type of power plant and any idea? Yeah.
To generate electricity, yeah?
Yeah, to generate electricity only, but where exactly? Can you guess, or I mean, do you know this, or
No, sir.
you might have seen this actually in rural areas? You have these sugar mills, right? So that processed sugar cane. So most of these sugar mills use the bagasse from the sugarcane itself to produce power and heat required for the sugar mills itself, right? So they crush the sugarcane, the bagasse that is left out, okay, the waste that is left out from after crushing sugarcane. So that is dried first, and then that can be used as a fuel. So it's most of this is bagasse CHP, the combined heat and power. Okay, so it's captive basically. It's not being used, or it's they're not transmitting that power to the grid. So biomass, so it's not very widespread. It's only in some regions it is captive. That's it. And in another case, these rice mills where they separate the husk from the rice, right? The grain. So even there, they use the rice husk to generate power for their own requirements. So this is where biomass is being used at present. Okay, there were more biomass power projects that actually failed over the years because of majorly because of the availability of biomass. The biomass is available in abundance, but then it has to be available to that plant, right? So that was an issue. So there was a demand and supply gap between where the biomass is generated and the demand center of the biomass. So that's where the issue was. So if you look at the installed capacity, it's around 210 gigawatt. Okay, and out of that, about 40%, right? So here wind is like 40 gigawatt and solar is 57 gigawatt as of July 2022. Okay, but this does not exactly paint the whole picture, and I'll tell you why. You have to look at the electricity generation over a period of time instead of just looking at the installed capacity. And if you look at the electricity generation, over 80% of the electricity comes from coal, despite having only 50%, or let's say 60% of the total installed capacity. Over 80% is generated of electricity is generated from coal. Okay, and only about 10% is generated from renewables, despite having, like, as you've seen here, like 40 gigawatt and 57, so about close to 100 gigawatts, right? 100 gigawatts, but it's only 10% of the electricity generated. Why is that so? Any idea? Anyone?
Sir, it keeps fluctuating.
Yeah, that is a simple answer, but there is a specific terminology for that. Do you know this?
Like for the fluctuation.
I mean, in general, like the usage of this, like,
Like water is not available in the dams throughout
I
the
mean,
year, and
this doesn't concern hydro. Hydro is like available most of the time whenever it's on demand, right? So if you
uh-huh.
have a perennial river, then hydro is basically available for you throughout the year.
Uh-huh.
Okay, but the problem is with solar and wind, and
Yeah.
to some extent biomass. But even biomass, that problem can be mitigated if, like I said, that demand and supply gap is bridged.
Mhm.
So why? Okay, solar and wind, like you said, the fluctuation that comes into picture, but there is a specific terminology of why it has such a low, mm, electricity generation
Contribution.
compared to coal.
Yes.
What is that terminology called? Any idea?
No, sir.
Okay, so there's something called capacity utilization factor. Have you heard of this term like before?
No, sir.
Okay, no? Okay. So capacity utilization, I'll cover this in the next few slides. So this is basically what it means is you have installed something. So it is in an ideal world, let's say you have installed 1 megawatt solar power plant. Okay. In an ideal world, let's say there is sunshine 24 hours a day, then it should generate 24 megawatt hour of electricity, right? So 1 megawatt times 24 hours will give you 24 megawatt hours. So that is the maximum that this plant would generate. Okay. But in reality, it is only generating about what 5-6 megawatt hour, because even though sunshine is available for, let's say, 8-9 hours a day, overall, like, okay, there are some fluctuations even during the daytime, right? So so effectively, it's about 5-6 hours a day. That's it. Okay? So the capacity utilization factor in this case will become 5 hours over 24 hours, which is about 20%. So that is the capacity utilization factor for solar. For wind, it's slightly higher because it doesn't exactly depend on or directly depend on the sunshine hours, but rather, so even at night it can generate depending on the wind speeds and stuff. I think it's about 30%, something like that. Okay. So the need for renewable energy. So there are these representative concentration pathways. Okay, so what do these mean actually? So this is the IPCC, Intergovernmental Panel for Climate Change report that came out in 2011. That kind of mapped all these scenarios of energy integration over the years. Okay, so this was in the year 2000. Like, what is the primary energy use by source? Okay, so you have coal, oil, natural gas, nuclear, bio, hydro, all of these things. And then these are the future scenarios. So what will happen if we move on this path, basically? So here this RCP 8.5, so 8.5, what do these numbers mean? The 2.6, 4.5, 6, and 8.5. So this is just so we speak about global warming, right? So it is the heat flux that is trapped by the atmosphere. Okay. So it is measured in watt per meter squared. Okay, it is the heat flux that is basically trapped in the atmosphere because of the greenhouse gases present in the atmosphere. So in this case, you have like 2.6 watt per meter squared that is trapped, then 4.5, 6, 8.5, and so on. So if we move across this pathway in RCP 8.5, that is very heavy on coal and then very little contribution from the other sources. Whereas if you look at RCP 2.6, it is a balance of everything. So you have bioenergy, which is playing a very major role in this case. And what happens if that is the what happens if we proceed in this fashion? So this is business as usual, RCP 8.5. So as we were in 2000, if we proceed in this pathway, what happens is uh, the temperature rise by the end of this century will be about 4 to 5 degrees Celsius. We are trying to limit it to 2 degrees or less than 2 degrees. And in fact, scientists argue that it should be less than 1.5. But then the political consensus is like, okay, let's limit it to 2 degrees from the start of industrial revolution. So whatever the atmospheric temperature was at that time, plus 2 degrees is the target right now. And if we have to move, if we have to achieve this, we have to move in this pathway in RCP 2.6 instead of RCP 8.5, which is business as usual. And if we actually move, if we actually have like a 5 degree, 4 or 5 degree increase in the temperature of the earth, there will be unbearable consequences. We're already seeing it. There are some areas with high rainfall and I mean unprecedented rainfall, like we saw in Wayanad recently, right? And in fact, every year in the Northeast, it's an issue. Northeast, Bangladesh, that whole region, it's a big issue in the past few years because they all get flooded. Northeast, still it's okay because it's in mountainous terrain, the water kind of runs off. But since Bangladesh is in the valley, right, it's in the plains, they have a lot of flooding every year because of this. And in fact, a few years earlier, Maldives had thought of buying land in India to settle their people so that, when inevitably their islands sink, they'll have a place to stay. But then that plan was dropped. I think now they are buying land in Australia. So that's how dire it is. Right. So we need to target this one, like less than 2 degrees. So
I
yeah.
have a
So coming to
question.
yeah,
So, whatever you said about RCP 8.5, is
yeah,
that the current trend? Like, what is going on? Like, the amount of coal
absolutely.
usage at present?
Ab- yeah, absolutely. So you just saw in the previous slides, right? You see here,
Yeah.
80% is coal.
Okay.
So
Yes, yes.
this is the direction that we are moving in right now. Okay.
Okay.
So we are
Yes.
very heavy on coal and very little contribution from anything else. So even the other non-renewables, if you can see, there is a good reason for that. Okay, I'll come to that in a while. So there is a good technical reason for that. Okay, but then we can't
Yes, sir.
exactly do that indiscriminately. That's what I'm saying here. Okay,
Mhm.
so
Yes.
I'll explain why this is. Okay, in a while.
Okay, sir.
Uh, So yeah, so coming to solar photovoltaics, so there are. So has anyone had any experience with solar so far, or any? You might have gone on a field visit, or maybe an internship, or whatever it is.
Sir,
Yeah.
my house runs on solar, sir. I helped my father install the whole setup.
Oh, awesome. So it's rooftop. And do you have net metering or?
No, sir, it is rooftop. Right now
Yeah.
we have four solar panels
Okay.
of about, I think, one by one meter, and
One by
it's
one. One by one came very long ago. I think about 10 years ago. It might have been. Or when did you install this?
it was installed about 2 years ago, sir. One by one.
It
I mean,
might
I'm not aware of
it,
any of the specifications. I'm talking about
it
the
might
size
be
of the
two by
solar
one.
panel.
2 by 1 it should be.
Yes, sir,
Close to two
maybe.
by one. It's 1.9 by zero point 0.9, something like that. So those are and what
Yes, sir.
modules do you, what make of modules?
Uh, I'm not aware, sir, because my
Okay.
father brought the solar panels
Okay.
from his like workplace, which is overseas. But
Oh,
right now, only the um, how do I say it? I think the light duty electricity works in solar, like the fridge and
yeah.
all that works
That's
on grid electricity.
normally that is the case. Like it's very similar to how you use an inverter and UPS at your place. Okay, so when you don't have electricity, it's only the lights and fans and these kind of light duty appliances that work. So your heavy duty appliances won't work when there's a power cut. And yeah, so you would have an inverter. So you don't have a battery bank, right? It's
We do, sir. We do. We have two
oh, you have a
batteries.
battery as
It,
well.
yes, sir.
Okay. Oh, so okay. So you would have converted. You'd have, I think, connected that to your inverter and UPS supply, right?
Yes, sir. We have from the solar panels, it goes to the inverter and then to the
Yeah.
batteries and then
Hmm.
back to the inverter through to the house supply, sir.
Okay. Okay. So basically, okay. What you're doing is you're generating power and you're storing it, and then when you don't have power, you're using it from the inverter to the so from the battery through the inverter to the UPS, and you're getting the supply. That's how it is, right?
Yes, sir.
Okay. Okay. That's awesome. So it's standalone. So as you can see here, it's a standalone PV. It's not grid connected. So there are okay, there are two types of connections. So one is megawatt scale grid connected photovoltaic, and the other one is kilowatt scale kilowatt scale, that is rooftop. So one is ground mounted and the other is rooftop. So what he was explaining is about rooftop solar. Okay, and so the grid connected solar is basically you have all these big solar fields where you have. Maybe we were talking about power grid, a solar field yesterday, 2000 megawatt and this kind of stuff. Okay. So here from the solar field, DC electricity is generated. It's exactly like a battery. It works exactly like a battery. So you have a positive and a negative. DC electricity is generated. It goes to an inverter that converts it into low voltage alternating current. But that is in a very low voltage, like I said, it's around 220 volts that we get at our at our houses basically. So if you want to connect it to the grid or connect it to the substation, what you need to do is you need to transmit this electricity to the substation, but that requires stepping up of the voltage. So you need a step up transformer that converts it into high voltage alternating current, and then it goes through a transmission line, and at the substation there is a step down transformer. So you need to install everything, and so even so okay, it doesn't have to be at the substation. Basically, the substation will also be in the same voltage as the high voltage line. Okay, so you connect it there, and then from the substation, it goes to the domestic consumers, where there is a step down transformer close to your house, and then you have low voltage alternating current again, and it comes to your house. So this is how it works in a megawatt scale grid connected photovoltaic. When you come to rooftop, so what he explained was standalone. So I'll come to that in just a moment. So this kilowatt scale grid connected photovoltaic is, so you have this rooftop photovoltaic. So on your rooftop you install all these, maybe 4 or 5 panels, whatever it is. It goes through an inverter. Okay, and then there is an AC panel, or your switchboard basically. It goes to there, and then it goes directly to your load. So what happens is, in this case, your house is connected to the grid, right? So you're taking connection from the substation through the step down transformer. So in case you're not using it, let's say your demand is not as high as the supply is, especially during the day, for example. So what happens is, it bypasses the load. There is no load here, so it goes back through the same line to the grid. And there is something called net metering. So here, instead of having a single way meter, there is a two-way meter, an electricity meter that can measure energy in both ways. And it basically measures how much energy you have used from the grid, how much energy you have supplied to the grid from your solar panel. It just subtracts both, and then that's your final bill. Like, let's say you have used 100 units and you have supplied 90, you only have to pay for 10 units. So that policy exists in a few states. Okay, but right now I'm not sure which states provide this facility. Okay. So when you come to standalone photovoltaic, you're using it only for your own, electricity purpose, basically your own house. Okay, so you have a solar field. It comes to an inverter, and then it goes to the battery bank to be stored. And then when you don't have like when you have a load shedding or something like that, the battery acts as the power source here. So it goes back to the load through a UPS. Okay, it works exactly like how your UPS would work when there's no power supply. Right. So this is an inverter. You can, yeah. So this is an inverter. So this is a string inverter actually. This is for rooftop applications. This is a rooftop power plant, that is grid connected rooftop. And this is a ground mounted power plant. So these are all projects that I was personally involved in. So this one is in Chennai. This one, I think it's in Bidar. Okay, and this one is in this is also in Bidar. Okay. So coming to solar thermal applications, so solar thermal can be used for multiple purposes. So first, solar PV can be only used for electricity production, but solar thermal can be used for multiple purposes, including water heating and electricity production. So this is for water heating application. You have two kinds of collectors. So one is flat plate collector and the other is evacuated tube collectors. So flat plate collectors are, you might have seen this. Many of you might even have this installed in your houses, right? And so you have this inclined plate which is coated black to absorb the maximum radiation, and it is glazed, okay, to trap the maximum amount of heat within, and then the working fluid is within tubes, within pipes inside this black coated uh, plate basically, and then it's insulated at the bottom. Okay. Evacuated tube collectors, on the other hand, what happens is there is a tube, and inside there is a pipe where the water runs through, and then the gap between the tube and the absorber plate of the pipe is evacuated. That is, there is vacuum in between. So this kind of improves the efficiency of the heat transfer. Can someone explain why? I think you're all mechanical students, most of you. So can you explain why vacuum increases the efficiency? Yeah. Anyone?
Because the air medium is not there, and air actually kind of cools it down.
Yeah, but that is true. But I mean, I need a more technical explanation for this. Like, why are there less losses, heat loss? Basically, why is there less heat loss because of the vacuum? The point you said about air is right, but there's some specific thing that you're missing out there.
I'm a CS student, that's why.
Sorry? Oh, okay,
I'm
okay.
not a
I mean,
mechanical student. That's
yeah,
why, I guess.
mechanical or chemical engineering. Anyone from mechanical or chemical can answer this question.
Because
Yeah.
Sir, I think it's because in a vacuum the gases don't move around as fast, so there is not a lot of heat lost in, like,
There
it's
is no
not
gas in a
consumed.
vacuum, right?
Yes, sir.
Yeah. The vacuum is like, I mean, you're moving literally anything that is there. Okay, I'll give you a hint. Have you all had your heat and mass transfer courses already? Someone's trying to say something, but I'm not hearing anything. Anyone? I'm not able to hear. Is it just me or?
No, sir, no one's talking actually, I guess.
Yeah. No. Someone had their mic unmuted and then there was some disturbance in between. So I thought someone was trying to speak. Okay, mechanical students, I mean, heat and mass transfer. That's the hint that I'm going to give you. So please explain why, I mean, what in heat
sir,
and
am I
mass transfer?
audible?
Yeah. Yeah, please go ahead. I can't hear anything. Why is no one able to answer this? This is very simple.
Sir, in vacuum, it has more heating,
Yeah,
like
that's what I'm
more.
asking. I'm asking why. Why is that so? I have an answer on chat. Let me just check. Heat loss through conduction is eliminated, but is it conduction? Are you sure it's conduction? So what is conduction? Conduction is like you have surface to surface transfer, right? Yeah. Convection is the right answer. There is no conduction here. Even here, there is no conduction. Conduction is happening between the I mean the surface of the tubes and the water itself. So there is conduction there, but there is no conduction happening between the layers, right? So it is convective heat transfer because the air here is moving. It leads to convective heat transfer. Yeah, there is no medium. And that's why there is less convective heat transfer in this case. Okay, so there is only radiation. Conduction still happens. Conduction still happens between, the surface, exactly, like the surface of the pipe to the fluid and all of that. But from this tube to the plate, there is no convection happening. And that's the reason why it is much more efficient. Okay. So solar thermal for power applications. So we have seen the water heating applications. So these collectors, they are non-concentrating. The ones that you saw here, right? They are non-concentrating collectors. They just collect the heat from the sun directly. Okay. But over here, you have concentrating collectors. So for example, parabolic trough. So it's in the shape of a parabola. And if you recall, the parabola has a focus. Okay. So whatever rays of sun fall on any point on the parabola will, it will fall this way and then it will go directly to the focus, the point of the focus. So we run a pipe through that focus wherever that focus is. And then there is a heat transfer fluid there. So because the entire thing is like concentrated on that focus on that focus point, right? So the temperature is very high in this case. And similarly, there is a central receiver where you have heliostats, the flat mirrors basically that concentrate. It's not concentrating exactly. Each mirror will just reflect the sunlight directly to a tower. Okay, there is a tower, and on top of this, there is a heat transfer medium. Okay. And so because there are so many thousands of heliostats that are placed around the field, they all the rays of the sun are all concentrated at the top of this tower, and it reaches like more than 1,000 degrees or something like that. That's the temperature over. And this one is compact linear Fresnel. Fresnel is like, again, there are flat mirrors, but instead of having like a small mirror, it's like a one complete row of mirrors. And then over here, it's very similar to this, but then here you have like one row of collectors basically on the top. And these mirrors are focusing onto this row. And then again, you have high temperature because of this concentration. And parabolic dish, yeah, you have a question or? You've raised your hand, right? Okay. Let me continue. Okay, parabolic dish is basically you have a complete parabola. Okay, here it is like a half parabola. This one is like a dish. That one is like a trough. This is like a dish. So there is a point focus. And if you place anything on that point focus, it will become extremely hot because it's focusing the entire, uh, you know, okay, network issue. Okay. The entire sun's energy onto that point. So normally parabolic dish is actually pretty efficient, but then it's not so much in use. What happens is we normally use Stirling engines. So a lot of you might know what a Stirling engine is. Stirling engines are placed right there, and using the heat generated over there, the Stirling engine will generate electricity. Okay, so I think I have what second. Okay, I'll just explain how power is generated. So basically, you have all these phase change materials or heat transfer fluid. Let's take the case of this parabolic trough, where you have this pipe where there's a heat transfer fluid. That heat transfer fluid will reach about, I think, 500, 600 degrees Celsius, and there is a heat exchanger at the end of it, where you have water, and then the water is converted into superheated steam at high pressure. Okay, then you have your normal, the Rankine cycle. Okay, so you have the same Rankine cycle that you have in a thermal power plant, okay, with the turbine and condenser and everything. But instead of coal providing you the heat required, it is coming from concentrated solar energy. That is the only difference between this and a thermal power plant. That's it. Okay. So these are some of the features of these different kinds of collectors. So you can see the operating temperatures about up to 550 degrees Celsius. So this one is lower. Can go up to 565. This one is lower. The compact linear Fresnel, because it's not very effective just having flat mirrors focusing on um, top of a line. Okay, and parabolic dish, like I said, it is very high temperature because of the high concentration. Okay, and it has a very high efficiency as well. Okay, and the capacity utilization factor, I was just talking about it. So it's between 25 to 28 for, or in that range for these three. And for central tower, it's about 55%. So that is pretty good actually, 55% annual capacity factor. Okay. And you can see the concentration, how many suns, the energy of how many suns, like you have one sun and then you're focusing it. So how many suns can it lead to? So if you look at this parabolic dish, it has more than 1,300 suns. You have the energy of 1,300 suns on that particular point. So that's how hot it gets there, right? And similarly, in the central receiver, you have more than 1,000 suns. Okay. So there are some fundamental differences between solar PV and thermal, but can someone tell me some differences? Like one difference I already told you about, but let's have some from the audience as well.
So in
Yeah.
photovoltaic cells are used, and in thermal vacuum tubes are used.
Sure, but I mean in terms of utility or in terms of its operations and that kind of stuff. The utility, like I said, PV can only be used for electricity generation. You can't do anything else with it. Thermal can be used for both water heating or just heating purposes and uh, electricity as well. Okay. Any other
Yes.
any other differences that you know of or you can think of? Okay. Okay. Let me just run you through this. So there is the radiation, right? The solar radiation, they are of two types. One is direct radiation, the other is diffused radiation. Direct radiation is basically what comes from sun directly to the earth. I mean, it hits the earth directly because there is nothing else in its path, no clouds, no other particles, and it comes directly. Diffused radiation is when you have, let's say, some clouds are there, some particles are there, there's some pollution or something like that, it gets scattered. Okay, so that is what is diffused radiation. So the difference between direct and diffused radiation is direct radiation is what heats up the ground or heats up whatever it hits because it's directly hitting, right? Diffused radiation loses some of its energy to these particles when it comes, right? So solar PV uses both direct as well as diffused radiation, whereas solar thermal uses only direct irradiation. Why is that so? Because solar PV uses the photons that fall on the surface of the plate, right, of the panel. Whereas solar thermal will use only the infrared spectrum that kind of heats up the surface that it hits. Okay. And solar PV produces DC electricity. It acts as a battery, like I told you. There's a positive and a negative. Whereas solar thermal can produce both DC and AC depending on what kind of generator you use. Okay, so you can even use a DC generator to produce DC electricity if you want. Okay, or you can produce AC electricity. Okay, and like I said, it can only produce electricity. Solar PV can only be used to produce electricity, whereas solar thermal is can be used for heating as well as electricity. Heating, in fact, it can be used for cooling as well. There is a specific technology that can be used for cooling that is called vapor absorption refrigeration system. Has anyone heard of this? Vapor absorption refrigeration. So there is compression refrigeration that you would have heard of, what air conditioners and refrigerators work on. So there's something called absorption refrigeration. Anyone? Again, mechanical students. No one? Okay. So basically what it does is, so you have a generator where, okay, you have a mix of refrigerants here. So in case of our normal refrigeration, in compression refrigeration, you have a single pure fluid that runs, right? So it gets compressed, then condensation, then evaporation, and then, uh, yeah, so all of this happens, right? But in case of vapor absorption, what happens is there is a mix of there's an azeotropic mixture, basically, azeotropic mixture of let's say ammonia and water, for example, or lithium bromide and water, for example. So one is the absorber and the other is the refrigerant, absorbent, and the other is refrigerant. So I'm not going into the details of it. So the basic concept is you use heating, you use the energy from the heat itself to affect the cooling. So it's a very neat concept. So if you can just look it up, it's very interesting actually. Okay. And then solar PV, you have flat receivers, and solar thermal, you have concentrated receivers. So these are some of the differences. So coming to wind power, so you have this is pretty straightforward. So you have high wind speeds. In places where there are high wind speeds, you have you need to go to a certain height, right? Let's say 70 meters, 100 meters, and so on. Okay, that's where you will have uninterrupted winds. If you place it at ground level or just above ground level, then what happens is there are lots of disturbances, so it won't work that way. You go to these heights, and then the wind kind of pushes these blades that runs a shaft and a gearbox. There's a gearbox to convert. I mean, the RPM is very low for the wind turbines. Okay, so with a gearbox, you are just increasing the RPM. Okay, there's a generator which generates electricity, a synchronous generator which generates electricity. And the tower on which it is located is, you can adjust it. So there is something called yaw control, the pitch control and all that, where you can, adjust it based on the wind direction. And then if you want to stop it altogether, you can keep it stopped also. Like if there is a tornado or if there is a cyclone where the wind speeds exceed like 25 meters per second, then normally the wind turbines are stopped because it's not safe to operate the turbines anymore, right? So the power generated is directly proportional to the area swept area of the rotors, the air density, and the power coefficient, and the cube of the wind speed. So this is basically the formula for calculating the power generated from a wind farm, basically. So CP is the power coefficient. So the maximum power coefficient can be 59.3%, which is called the Betz limit. So you cannot extract more than 59.3% of the kinetic energy of the wind. So that is the scientific principle here, right? So some concepts and definitions. So I was just telling you about why it is, why we are following on the path of more coal and less everything else. And there is a specific reason for that. So in power generation, there are some terminologies that you need to know. So there is this base load and there is peak load. So what is base load? It's basically the absolute minimum amount of power that is consumed anywhere. Like let's say in a city or in a town, let's say the demand is like 100 megawatt, but the absolute minimum demand that you need at any point during the day is like, let's say 20 megawatt. Okay. So you need to provide that much power no matter what. So this is the absolute minimum. So for 24 hours in a day, you have to provide 20 megawatt. Okay. Whatever goes above and beyond that is like comes under peak load, right? So that is fluctuating. So base load is like a stable demand. So this much demand will definitely be there. Whatever goes above and beyond is peak load. Okay, and so there is. So how do you plan for this? Like, okay, for base load, you need some source of energy that is stable, absolutely stable. And for peak load, you need something that is flexible. Okay. So what can be used for the base load? Can someone answer? You need a totally stable source of power for the base load. So there should be no fluctuations. There should be no. It should be completely reliable. Okay, and it should be able to provide the same or at least a similar and above, right? So let's say 20 megawatt, it has to provide at least 20 megawatts at all times. Yeah,
Thermal, sir. Thermal.
thermal. Yeah, basically that's the idea, and that is the reason we have so much of coal right now, because the base load is absolutely essential. If we don't give the base load, then we are at the mercy of the environment. Basically, we're at the mercy of nature. Okay, so if we that and that's the reason we can never completely do away with thermal power. I'm not saying it has to be necessarily coal. It could be replaced with biomass as well if there is a reliable biomass supply for these coal power plants. Okay, the same coal can be replaced by biomass, and then now we have a renewable source of base load. Okay, so and that is the reason biomass is very important, because now even NTPC and many other organizations, they have started. They have these policies of co-firing coal with biomass pellets. Basically, that has started about 2-3 years ago. So now for the peak load, what happens is you need something that is flexible, totally flexible. Okay. So what could be an example of that? Flexible, but it has to be completely reliable. And so what can we use for peak load?
Solar or hydro?
Hydro can be used for, yeah, hydro is, yeah, one example.
Hydro, like perennial rivers.
Yeah, perennial river. The hydro can be used for both base load as well as peak load. Okay, because hydro can be controlled. Okay, so if you want, like, absolutely, you want the same power throughout, you can do that. If you want to increase it to match the peak load, you can do that. So hydro is one. The other is gas turbine. Okay, natural gas power plants. Okay, so that can be very flexibly. In fact, you can go from 0 to 100 megawatt energy fee like in a few seconds. You can't do that with coal. So coal can never be used for peak load. Or basically, thermal power plant can never be used for peak load, because the startup itself will take maybe hours or even days together to reach that level, and then reach steady state. It will take either hours or even days. Okay. So thermal can only be used for base load. For peak load, you can use either gas or hydro, or even diesel generators. Some people may use. Okay, so these are some examples. So when you're planning the supply for any city or anything, so you need to keep in mind a few things. One is the firm capacity. Let's say your demand is, let's say, 100 megawatt. You need to ensure that there is at least you're installing at least 125 megawatt. Like, you have 25% overrating basically. Okay, but that comes there's a catch here. Let me ask you this. So I have a 100 megawatt demand in my city. Can I install 125 megawatt of solar? I just told you that I need to do a 25% overrating. So I'm saying that I'll cover the entire thing by solar PV. Will that work?
No, sir.
Why
Like
not?
you talked about the factor.
Yeah, the capacity
You
utilization
talked about
factor,
the
but
capacity utilization factor.
yes, but there is another thing here, which is the capacity credit, which is denoted by this epsilon C. So what is capacity credit? It is nothing but the minimum power that it can generate at any point throughout the year. You're running the plant for the entire year. What is the minimum power it can generate? Okay, the absolute minimum. So what is the minimum for solar or wind, for that matter?
0.
Exactly. 0. So if you look at this formula here, so you basically add up all the sources, okay, the installed capacity of all the sources, and then you kind of multiply it with the capacity credit of each of these sources. Okay, so if you do that for solar, then obviously your firm capacity is 0 here. So even if you can install even 1000 megawatt, you're not doing anything. It's like, having a Ferrari and driving it in Bangalore roads. Okay, so theoretically it can
Yes.
reach 300 kilometers per hour, but then you'll still take about 1 hour to reach 3 kilometers. So in reality, your average speed is only 3 kilometers per hour. You can do that even on a cycle. Why do you need a Ferrari car for that? Right.
Yes. Yes. Yes.
Right. So yeah, so that is basically the firm capacity. You need to keep in mind the capacity credit. Okay. And then so when it comes to coal, basically you cannot when it's running at a certain load, you cannot run it below 30% of its full load capacity. Okay. So there's also that. So that is also one reason why coal will never fade out, or a thermal power plant will never fade out, because if you run it below 30% of its total load, right, of the plant load, then what will happen is, again, you have to go through that entire thing of startup and then coming to that full load and everything. So it's very tricky running a thermal power plant, basically. Okay. And the capacity utilization factor we talked about, basically, it is the amount of energy actual generation over the year to the theoretical generation. So if you have a 1 megawatt power plant, let's say solar, and it's supposed to generate 24 megawatt hour in a day, or 24 into 365, whatever that is. I think, yeah, it's about 8760 megawatt hour in a year. Okay, but it generates only like 5 megawatt hour in a day. So the capacity utilization factor is about only about 20%. Okay. So we are at the end right now. So if you have any questions, first we will do that, and then we'll move on to the Q&A. Any doubts or any questions?
Sir,
Yeah.
that is the what is that? You spoke about the RCP 8.5, and
Yeah.
we have to get it down to RCP 2.4, right?
2.6. Yeah.
2.6, 2.6. So the main reason for this webinar is to try and get to try and make us understand how it can be done through biomass. Like biomass
Yes.
is the next steady source of energy, right?
Yes.
Yes, sir.
So 2.6 has a very high portion of bioenergy, if you see here.
Yes,
right?
yes.
So this is very
So
important
that will
in the
be
context of the future.
yes, sir.
There is still
Like you
coal,
told about
like
the
I said.
supply versus demand.
Yeah,
Right?
so the supply versus demand is basically, there are lots of bottlenecks when it comes to the biomass supply chain. Okay, so for
Yes,
one, the
yes,
biomass supply chain is like widespread and it's distributed. It's not like coal where you have some mines and then from there it's not like point to point like coal or natural gas, right?
yes,
So you have to go to
yes,
each village, each farm, and then you have to beg them like, okay, please give us your residues. Or if you're like, let's say, planting some, you're doing some plantation, let's say, okay, to harvest the wood
yeah,
at the end of, let's say, 3 4 years, whatever it is. So you need to be sustainably doing that. Otherwise, then there is no point of doing it, right? So there are a lot of issues when it comes to the supply of biomass, which is why none of these projects have actually worked. Okay, the supply of biomass
yes,
is a very huge thing. Like it's a huge problem.
Because land is fragmented and yeah.
Yeah, land is fragmented, and then there are lots of political issues also, right? So,
Yes.
like for example, the farmer may not be willing to give you that biomass. He may use it for some other purpose, or even if he's not using it, he may just not be willing to give it, and he may not give you any reason. It could be some political pressure from his peers, or I mean, whatever it is, right?
Yes. Yes.
And there are also logistical issues. Like I said, it's because it's widespread and it's distributed. There are logistical issues, and there are seasonal issues also. So the most, so if you take Karnataka, for example, there are 3 seasons of agriculture, right? So there is Kharif, Rabi, and summer. So most of the biomass that is available in October in the Kharif harvest season. So out of 100%, you have 95% available only in that season. So you have to store it completely so that you can use it for the rest of the year. So there are all these logistical issues that come into biomass. So when you're formulating any policy for biomass, right, you need to consider all of these issues, all of these bottlenecks in the entire value chain. Only then it will work. So most of these biomass policies do not consider this. They just assume that by providing some subsidies or financial assistance to these companies that are installing these plants, it will just start working. That's not how it works, right?
Yes, sir.
Yeah. So that's the issue with biomass. I mean, if you want to replace coal with biomass, then you need to tackle all these issues. So any other questions? Any other doubts? Okay, so let's move on to the Q&A. So which of the following statements are true for a megawatt scale grid connected power plant? You can read the options and let me know. Anyone?
Sir, option B, A, B.
It's megawatt scaled grid connected power plant. So you can read the options again
Sir,
and
option A maybe.
okay, why is it option A? I mean, whatever answer
Sir,
you're giving, you
because
just have to justify it.
so megawatts need a supply of transformers. It could be it has to be step up and step down. Transformer should be used. So, but the B option is that it is megawatt, so much amount of power is generated. So I think we cannot store that amount of power in batteries.
Yeah, but
So
the
I think it should be transmitted.
Keyword here
Yeah.
is grid connected. So if it is grid
Yes, sir.
connected, you do not need batteries.
Yeah.
So if it is
So
just a megawatt scale power plant, you could have
yeah.
batteries technically, but then
Yes, sir.
those would cost a lot of money. It's going to cost a bomb, actually. Okay.
Yes.
And where will you have this battery bank? So if you, let's say you have a megawatt scale means it could be like 50, 100 megawatt. Where will you have the battery bank? Where is the land, right? To have a battery bank that size. And the second thing
Yes,
is
sir.
that these batteries have to be replaced once in every 2, 3 years. They have a cycle, right? Maybe they have like 1,000 cycles of charging, discharging, 1,000 to 2,000 cycles. So about 4 years, even if you consider one day per cycle, that's about 4, 5 years. You need to replace all these batteries again. So it's like a recurring cost and it's very expensive. And that's the
Yes,
reason.
sir.
That's the reason we have these grid-connected power plants. And I mean, the batteries, the storage based power plants are not very popular, so at least in large scale. And in small scale, of course, you can do it at your own house, like we had an example earlier, right?
Yes.
Yeah. So what's the answer?
Sir, option A.
Yeah, absolutely. So because it's grid connected, you need transformers to match the voltage of the transmission line, and then at the uh, point of use, you need to have another transformer to step down that voltage and then distribute it to the houses or wherever it is used. Okay. Right. So what is the advantage of evacuated tube collectors over flat plate collectors?
Sir, option C.
Yeah, why? I mean, discuss this, right? I mean, the convection
Yes.
losses are
Yes.
lower because of the evacuation, right?
Evacuation. Yes, sir.
Yeah. Question 3 is which of the following statements are true? I don't think I told you about storage in solar thermal power plants, but okay, you can let me know the option, I mean, which is the correct one, and then I'll tell you about that.
Sir, what is non-concentrating collectors?
It's just flat plate. I mean, you're not concentrating the solar energy onto a point or onto a line, something like that.
Huh.
So you have all these flat collectors, right, that do not actually concentrate the energy of the sun in any fashion.
Sir, option B. B.
Right. Why is it not option A? Can someone tell me?
Just like you said a few minutes ago, like storing the power generated in batteries is
Yeah.
not
But
feasible
in general,
economically.
can energy be stored in a solar thermal power plant? In general, I mean, I'm not even talking about batteries.
Okay.
In any way, can you think of it? I didn't tell you this, but yeah, I'll tell you shortly. But can you
Okay,
just
so
guess?
because the energy is in the form of heat, so heat cannot be
Yes.
stored in batteries.
Yeah, heat cannot be
Right?
stored in batteries. Yeah, but can it be stored in general? Okay, I'll just tell you this. Okay, so a lot of heat is generated in solar thermal power plants. So what happens to it at night? Because you have a lot of investment, a lot of equipment riding on this, right? So you cannot just generate during the day, like in the case of solar PV, and then let it go. Okay. So what we do is there are some there are these materials called phase change materials, which kind of if they take in heat, they'll change the phase, maybe from solid to liquid or something like that. Okay. So you have these huge tanks which store these phase change materials, and then the heat is transferred to these phase change materials, and the heat is stored in that. So when this I mean, during the evening and night times, right, when the radiation levels are low, what happens is the heat from the stored heat from these phase change materials is again used, okay, in the same process. Okay, so instead of the solar field now, the solar field is useless now at night. But then this stored heat can be used again in that heat exchanger, convert water into steam, and then the same Rankine cycle will continue. And based on, so you can have the irradiation data for any region, like let's say, take Mangalore for example. What is the direct irradiation data there? And then You can decide that, okay, the maximum number of days without or cloudy days, let's say let's take for example, let's say it's 5 or 6 days at a stretch. Okay, this is the maximum it can go. So you design the heat storage in such a way that it stores like 6 days of heat. So you don't have to stop generating basically in those 6 days of cloudy weather. So because when it's cloudy weather, the solar PV will still generate electricity because there is still diffused radiation. But the solar thermal plant will stop generating because there is no heat. Okay. So basically, yeah, B is the right option because you don't need concentrating collectors for solar water heating applications. What is meant by CUF, capacity utilization factor? We've spoken about this.
Sir, option A.
Yeah, why is it A?
Yeah, because it is the ratio. Like if we have an ideal value for example, solar panel, solar photovoltaic, it will not generate the generate if it is like 1 megawatt. It won't exactly generate 1 megawatt. It will
It
be
may
much lesser
generate
than that.
1 megawatt. So it's not like it won't generate 1 megawatt exactly. It's like it may generate 1 megawatt at certain times during the day or during the year. Okay. But it
Yeah,
won't
yeah,
generate 1 megawatt at all times. That is the whole
yes,
definition. Okay.
yes.
And in fact, you cannot reach 100% CUF even for thermal power plants. Do you know why? Can you give any reason why?
Loss
So, I
of
mean,
heat.
no. I mean, it has nothing to do with heat. It has everything to do with how at full load, how many hours you are running during the year. Theoretically, you can run the coal power plant 100% of the time, right?
Yes,
But
yes.
even the coal power plant will not have 100% CUF in practicality. And why is that? Any idea?
Lost during transmission.
No, that has it's everything to do with the operations of the plant only. There is nothing after that. There's nothing before that. It has everything to do. The CUF has everything to do with the plant itself.
Like you said, with thermal, there is a problem that it takes a lot of time to start.
Yeah. So let's
Is
say that you
that
have
accurate?
started it. You have started it now. It has reached a steady state. Now you are running
Yes,
it for the entire year.
yes.
Okay. So theoretically,
But
you can
at
reach
times it
100%.
might require a peak load, and
No,
in order
I mean,
to
the peak load will come on top of the base load, right? So base load is always there. So no matter what, so if you're consuming, your minimum consumption is 20 megawatt and your peak
yes,
consumption is, let's say, 60 megawatt. Okay.
yeah,
So,
yeah,
but that 20 is like a bare minimum. That 20 has to be there at all times. So 100% of that time, the 20 has to be generated. Okay. So anything
yes,
above
sir.
20, the 20 to 60 can be generated using other sources.
Okay.
So even if you have a plant, let's say you have a coal plant of 20 megawatt only, and then you're running it for 100% of the time, theoretically that's a CUF of 100%, right?
Yes, sir.
Think practical considerations, like, I mean,
No, sir. I can't think of.
it doesn't matter which plant it is, any plant will require maintenance.
Yes.
Any and all plant will require maintenance, and you have to run down the plant during that time. So let's say for 1,000 hours in a year, out of 8,760 hours, you need maintenance of, let's say, 1,000 hours. So that's like, so you have 7,760 divided by 8,760. That becomes your CUF for that coal power plant, right?
Yes, sir. Yes.
Yeah. So no plant will have, in practical sense, no plant will have 100% CUF.
100% uptime. Yes.
Yeah. Okay. So yeah,
Yes.
the CUF, this is the JET definition. Okay. So now you know the definition. You calculate this. I've already told you a couple of times, but yeah, calculate this. Calculate the CUF of a solar power plant. Anyone?
So,
Yeah.
so just a minute.
Mm-hmm. True. So I have an answer here. Can you tell me how you calculated? You can just write on the chat itself. I mean, if you're not able to talk, you can write on the chat in case.
Yes. Round off to 21% because 5
Yeah,
is
that's right. I mean,
generated
someone.
per day. And out of the 24 hours, it generates only 5 megawatt hour.
Yeah,
So 5
absolutely.
by 24.
Absolutely. So that comes out to around 21%. So in general, yeah, this is the benchmark. I mean, this is the ballpark figure of the CUF of solar power plants. It's around between 19 and 24. 24% is for solar plants with trackers, okay, that track the movement of the sun. So if they do that, that can reach up to 24%. But in reality, it will be around 21, 22%, that range. Right? And what is the capacity credit of a solar PV power plant?
So 0%.
Yeah. So because I mean the minimum power it can generate at any point in the year is 0%. Okay. But this is based on nature. I mean, this is not based on the maintenance or anything that I told you about earlier. And that is because uh, you can um, operate a coal power plant if you want 100% of the time, theoretically, right? What is the minimum it can generate? The minimum will be like 30% of, so you can run it down to 30%, right? So 30% of whatever full load capacity it is. So if you have a 100 megawatt coal power plant, then the capacity credit will be 30 megawatt, right? Which is 30%, right? Identify the two statements among the four.
Sir, all of the above.
Yeah, why is it so?
Power generated from wind is proportional to the rotor area. Like
So if you have written
the
down the
rotor area.
formula, so you'll know that that's Cp times half rho A V cube, right? If I'm not mistaken. So A is the area swept by the rotor.
Yes. V is the wind speed of wind.
Yes, V is the wind speed, which means higher wind speed will help generate more power.
More power.
Okay. And you know about the Betz limit, which is how much?
Which is 59 around.
Yeah, 59.3%. But that is the Betz limit. That is the theoretical maximum fraction of energy that you can extract from a wind turbine, right?
Yes.
And then so it's all of the above. Right. Next. How would you design a power supply system for a city if the options available to you are, these are the options: solar thermal with storage. So the storage here is the thermal energy storage, not batteries. Okay. You have coal, diesel, and natural gas. So which is the best way to do it?
Sir, option D.
Why is it so?
Option D, because as you said, with storage, solar thermal can provide a continuous flow of
Perfect.
which will help in the base load, and coal
Yes.
also.
Yes,
And for peak
absolutely.
load, as you said, natural gas can
Mhm.
reach peak load within a few seconds or
Yeah.
at a sooner rate compared to
Yeah.
coal.
Yeah.
Yes, sir.
Same with diesel. I mean, diesel can also, if you have seen a diesel generator, so it can reach peak load within a few seconds, right? So solar thermal with storage, that's the most important point. Without storage, of course, it's not not reliable at all. But
Not
with
at all.
storage, you can run it for days at a stretch, even without the sun, right? Even if the sun were to disappear for like 5 days, you can still run the power plant. Okay, so that's how effective it is, the storage part here. Okay, so that can be used for base load along with coal. Right? Okay, so that's it for today. So if you have any doubts, any questions, please go ahead and ask. So the final